Oh, man. Oh. A little something in my throat. Not going to make it. Class canceled. Just be terrible, wouldn't it? All right. Hey, well, it looks like it is start time. I want to get you guys started so that we can wrap this up. I probably spoke a little too long just about all those wonderful pictures that I know you were so excited about last time after the test. But I think they're neat to see. I think they're neat to see the railroad tracks buckled up and the SR-71 leaking fuel and all those good things here. But obviously there's never enough time to show you all the neat things. That's why you do all that wonderful study and that homework and the Google research, and that's why they say you're supposed to spend 2 hours studying for every hour you're in class. So I suppose if that's counting homework, you do more than that. If it's not counting homework, you probably do less than that, but I think it's counting homework here. Anyways, what I want to do is wrap up the discussion on Chapter 19 and then get into problems, and if we are so lucky, to even start Chapter 20. I know it's not on the syllabus that we start 20, but it would be great if we did. For this reason. I don't know if you've looked ahead, probably not too much. I know you've had a lot of tests this week. So obviously you had a test in my class, and so you had that Thursday, and I'll grade them this weekend and give them back to you on Tuesday. But if you're looking ahead, if you look into next week, I want to give you a little heads up here about next week. Maybe the good news, or I know you'll just cry when you hear this, if you looked at the schedule, there's no lab schedule next week. None for this class. And in case you are wondering why, it is because we are doing some interviews. Both Don and I will be tied up doing interviews most of Thursday and all day Friday and into Saturday. And the effect it has on you guys is that Thursday afternoon. Thursday afternoon, Don and I would be tied up, which is why we don't have a lab scheduled that week. So, including you guys on Wednesday, and again, Don and I will need that time preparing for the interview. So, anyways, that's why it's on the schedule. I thought about that back in December. Hope I make it through the 2 hours. Anyways, I wanted to point that out, and then also give you a little heads up, and here's why I'd like to start Chapter 20, is that's because Thursday we'll only have half a class. Thursday's lecture will be from 9 to 10. The first interviews Don and I give are at 10:30, so we've got to leave here, and we're going to actually kind of take over that lab room in PS 16. And so that's the last thing I want to mention is then, since we will be doing interviews in that room, it'll be all locked up. Students won't have access to it. You won't care. And that's 116, not 17, 116, okay? And that's the room you have the MC on Friday. So there won't be an MC on Friday is what I'm getting at for next week. Not tomorrow, but next week, all right? So next week, that's what I'm trying to say. It affects your class in this way. No lab, and that room will be locked up all day Friday, so we won't have an MC on Friday. Okay, I'll leave the 117 open, and so if you guys want to use the computers or go in there, feel free. But Dawn will be tied up that whole day. All right, well, as I said, there's just one more thing, extremely important thing, that I didn't quite get to here in 19, and we're going to see it. I know you saw it in 102. You probably saw it in your chemistry also, but it's called the ideal gas law. And so the very last discussion in 19 before we get into some example problems here, and then like I said, hopefully past the example ones and even a little start into 20 is what is called an ideal gas. And so here is where I will start. What do I mean by this phrase, an ideal gas? Well, we're back to our bouncing BBs that you saw before. I'll move this over. I mentioned it. Maybe you're starting to get to the point now that probably every day for our thermodynamics, we will have this demo in class. Because the mental picture to have here is what's going on a molecular level. What's happening right in front of you. All of these nitrogen and oxygen and water and carbon dioxide, but mostly nitrogen, right in front of you. If you could see it with your eyes, what would it look like? And this is the picture. They would be bouncing around. And so you can kind of imagine these as little BBs that have no interaction other than they collide. And so when they collide, there's a lot of force between them. Once they break off, there's no force between them. Now, that is what we call an ideal gas. A group of molecules bouncing around that when they hit, there's a lot of force between them. Once they separate, there's no force between them. Not quite true for those of you who know a little bit more about chemistry and those who went through 122 with the electric forces. The forces, you know, do interact even though you're not in direct contact. But the simplest model, and the one we will actually kind of derive as we get into chapter 21, is to say, what if you just had a bunch of BBs bouncing around? That is what's called an ideal gas. And so I will put three variables on the board here: pressure, volume, and temperature. And the three we've been talking about for, you know, some time here in this chapter. But as you look at this, I'm thinking you can see how these are connected together. What would this look like if I cooled it down? Well, that's probably what you would see, right? Less motion. The molecules move a little bit slower. But what else did you notice? Yeah, less volume, right? And so the volume is connected to the motion of those molecules. Again, not a surprise. That's what we've been doing, you know, last time we did the thermal expansion. Now we focus more on our solids and stuff, but this is a changing of the gas. Now the gas, though, being a little bit different here than the metals in the sense that there's a lot of empty space. So again, here's a mental picture of a gas bouncing around, empty space between the atoms. Whereas, as you'll see, coming up here in chapter 20, this is going to be our mental picture of a liquid, where there really is little to no space between the atoms. They're in the container. Of course, they're vibrating around, so maybe I'll shake them a little bit so you realize that they have temperature and they'd be shaking, but they're close together. And so squeezing a liquid doesn't really compress it much, or warming it doesn't really change its volume much enough. If the pressure's a lot, in fact, that was the discussion we had last time. What if the pressure was really a lot, where you could actually put a container and hold it down? And we said, you know, geology's like that, where a rock can change its volume by a factor of 2 between miles deep and up to the surface, and, you know, as it comes up, it'll crack. But in general, unless it's enormously large pressures, we say there's not much change due to temperature. A little bit, we've been calculating those. But you can't really change it with pressure unless you put a lot of pressure on it. That's totally different for this picture. A gas, it's got a lot of space between them. It doesn't take much push to change their volume. Their volume is very sensitive to pressure. And so, all three of these are then tied together. That's what I want you to see. If I were to raise the temperature, that means the molecules go faster. Now, if they go faster, that means they're going to spread out and have more volume. Or, if they don't spread out, then they're going to be in a tighter space, hitting harder, and have a greater pressure. Here's the idea of our equation. We like to say this: P, pressure. I like to start off this way. Actually, maybe I'll use the symbol alpha, although, just dawned on me, that might be a poor choice, because I mean this as proportional. Have you ever seen alpha as, you know, when you say something is proportional? Okay, so I don't mean the alpha of the thermal expansion that we've been doing last time, but what I mean pressure. Pressure is proportional to what? Yeah, and I'm glad you see it here. I would say one of the obvious factors here is its temperature, right? Because this is the motion of them. You make them go faster. That means they're hitting harder. And if they hit harder, that's where the pressure comes from? The pressure comes from these collisions. So I would expect the pressure in this gas to definitely be proportional to the temperature. But not only that, what else do you think? Oh, okay, I'd put those two together. I heard somebody say the number of atoms and the number of molecules. All right, so I'd put it this way. I would call it the concentration. I would say it's proportional to the number of atoms per volume. And I'd think of it as one factor. I guess we'll separate it into two here, a numerator and a denominator here. But I think mentally it's a little bit easier, at least it is for me, to think of that as one factor. And here's what this says to me. This says that the pressure is caused really for two reasons. The first reason is how fast are they going? The second reason is what's the concentration of them? How many do I have in this little volume here? And so if I increase the number, I get more pressure just because I have more impacts, because I have more molecules. On the other hand, if I increase the temperature, I have more pressure because I just have that same number hitting with a greater speed. So if any one of those two go up, and again you could say that this is really made out of two, and we will here in just a second, that is the cause of the pressure. And so there's what I'd call step one, kind of a conceptual feel. What is going on the molecular level? Why does the pressure and the volume and the temperature and the number of molecules all get related here? And so if we change an equation that says proportional to one that says equal, well, then I guess I need a proportionality constant. And I heard somebody say it a moment ago. It is a proportionality constant called the ideal gas law constant. And we give it the symbol R. And so this number is called the universal gas constant. How does it mathematically relate the number of molecules, the volume of the molecules, and the temperature? Those two or three factors, like I said. I like the two, but if you want to think of it as three, and I probably should just say three because we're going to separate it apart anyway, so I'll say three. But these three factors, number of molecules and the volume that they contain, and the temperature, those got to be related to the pressure. And so that's how it becomes an equation. Let me keep working with this equation, because the first thing I want to do before I even give you the number here is we should probably have some symbols here. Okay, and the symbol for the volume is probably the simplest one. We'll use V for volume. We've been doing T for temperature, of course. What is new is a symbol for the number of atoms. We're going to use a little n, except this is not really the number of atoms. This is going to be the number of moles. And for some of you that might be new. What's a mole? 6.2. All right. So the symbol we will use in N is an N, but 1 mole is a convenient way of grouping atoms. So we don't talk about how many atoms, because there's so many. We do the same thing when you go to the store. You don't buy 15 billion molecules of milk. You buy a gallon of milk. You group, and actually 15 billion wouldn't even be enough, but it's my point, billion, whatever it comes out to be here. But what you do is you group all of those into a new quantity called a gallon, and now it's convenient. 1 gallon, 2 gallons, half a gallon, 1.5 gallons, and so you don't talk about these enormous numbers. Moles are the same thing. It's a very convenient number. It's a very big number, but we like to label them in terms of how many moles do you have? Do you have 1 mole? Do you have 1 gallon? Yeah.
Why didn't they choose a base symbol?
Well, it actually is better, believe it or not, not to, because of this periodic table here, is that see those black numbers in there? Those black numbers, which you often refer to as their atomic mass, can have three important meanings. One meaning is it can tell us how many nucleons, that is, neutrons and protons. That's really the key. Because if you pick the number of neutrons, and then the question is, how many atoms would you have to have in order for that? Let's take nitrogen, which says 14. How many molecules would I have to have so that 14 means 14 grams? So the key is not so much to be base 10, but the key is to say, when I read those numbers, 1 mole would be 14 grams. 1 mole would be 12 grams. See what I'm getting at?
Couldn't they just change the number of grams and make that a base 10 number?
I guess you could have changed the meaning of a gram. Is that what you're getting at?
No. The number of grams that they weigh.
Oh yeah, but then they wouldn't correspond to the number of nucleons they have.
But they don't anyway. They're still off.
No. Well, they're only off. No. Oh, they're only off because those are the average. So, like if I take nitrogen, most of them have 14. But every once in a while, one of them has an extra neutron, and it has 15. It's not like one of them has 14.0067 neutrons. Is that making sense? Sort of? Kind of? All right, well, anyway, yeah, all right. But anyways, to have that number mean the number of nucleons, you have to have that be a number of moles. Yes, you do sacrifice a base 10. But anyways, but that's what's convenient about this number. It's a little weird number, and I think that throws people off. And it's not a base 10 number, but other than that, it is very convenient. All right, so anyways, it sounded from that discussion here that a lot of you have heard the word moles. We're going to use this symbol. We're going to use N sub A for this number, because it was discovered by Avogadro, if you were asking about the A. So this is often also referred to as Avogadro's number. What is or for us Californians, it's the avocado number, all right? But Avogadro's number here is this mole, okay? Now, the reason I say we're going to put it into the number of moles is because as I look closely at this proportionality constant must be listed in some kind of units, right? What units do you want to use? And I bet many of you have been exposed to this number, 0.00821 liters atmospheres over mole Kelvin. And so that's one way of looking at it. And it probably a way we never will in this class, but probably what you've been exposed to first. But if you look closely, here's what it's saying. It says as you look at this proportionality constant, your other units or your other quantities are in what units? In other words, the N is measured in what? Moles, exactly. And so that was our first conversation here, that we will label the number of molecules, not literally in the number of molecules, but in the number of moles, all right? And I know that from that constant, all right? But there's some other interesting things here. For example, what units would I use temperature in? Kelvin. Yep. And it's really not just because of the constant is in Kelvin, but because back here, we said the pressure was proportional to the temperature. Which of the temperature scales is motion proportional to temperature? Kelvin. Yeah, it's only the Kelvin one. So just looking at this, we can see right away that it can only be valid on the Kelvin temperature scale anyways. And unless you had like Kelvin plus, Celsius plus 273, then we could do that. But to write it as just directly proportional, where motion is proportional to temperature, right away it's got to be on the Kelvin scale. So make sure you use your temperature in Kelvin.
So was this equation only discovered after Kelvin, or what did they do before?
Oh, that's a timing question. I think it was after Kelvin, but I guess I'm not sure. No, I'm pretty sure it's, yeah, I'm pretty sure it's after, because it comes from the motion of the molecules. Yeah, yeah. Yeah, that's a good science history question that I don't know the order of the science. But the other two I wanted to be real careful here is what, using this number, what would be the unit for volume? Liters. Not very useful for us. We'll probably do cubic meters. So that's why I said we probably won't see this number often. And also pressure. What's pressure in? Atmospheres. So I'm going to do a little bit of unit conversion. I'm going to change this from liters to cubic meters, and from atmospheres to pascals. That'll be more useful to us. That's how we often measure pressure. And when you do that conversion, you might ask, okay, how many liters are in a cubic meter? And maybe I should ask, do you know? It's 1,000. Maybe we better go back to the definition of a liter. I guess it's really kind of chapter 1. What was or is the definition of a liter? Which also answers why we don't tend to use it too often here in physics, because it's kind of repetitive. I mean, why have units of liters when you have units of cubic meters, right? But what was the definition of a liter? Anybody know?
Is it 1 cubic centimeter one?
No, close. What's what?
1 milliliter is 1 cubic centimeter? Yeah.
Well, that's true too.
But a milliliter.
That's not the definition of a liter, but that's true. It's a consequence of the definition, right? Yeah, liter, you got it. Is what?
1 milliliter is 1 gram of water.
Okay. No, a definition of a liter is a box that is 10 centimeters by 10 centimeters by 10 centimeters. So that's the definition of a liter. So that's how I know, first of all, that if that's the liter, and if it's 10 centimeters by 10 centimeters by 10 centimeters, how many cubic centimeters is that? 1,000. So 1,000 cubic centimeters is 1 liter, so 1 milliliter is 1 cubic centimeters. That's what you were saying. The getting 1,000 here is fairly simple. If I take a meter stick, if I were to lay boxes that are 10 centimeters long, how many could I fit here? 10. How many could I fit here? 10. How many could I fit here? 10. And so 10 by 10 by 10 is 1,000. So I can get 1,000 liters in 1 cubic centimeters. Anyway, so if I do this unit conversion, it's going to change this number by 3 decimals. Question?
I remember the ideal gas constant is 0.0821, not 2 zeros.
Point, ooh.
1 second.
Oh, it is. Thank you. No, I meant to do this. Sorry. That's 0 point. Yeah. Yeah, thank you. So that would be 3 zeros. The other thing that I want to remind you of then is the relationship between 1 atmosphere and a Pascal. What was that? Yeah, I know, we're going all the way back to Physics 121, Lord forbid. All the way back to December.
Can we do momentum and energy over there?
Ah, you already did. What is it? Yeah. 101,300 pascals. In fact, maybe I should write it as 101,300 newtons per square meter, which is what a Pascal is when I do that. All right, so doing that unit conversion, we come up with a number that you'll see more often in this class is 8.31, because we will put things in pascals and cubic meters. In fact, we'll even simplify that. 8.31, what does this become? Yeah, might as well call it a joule, right? It's a Newton times a meter. And it'll give us some insight to where we're headed, because this is a pressure force. and a volume. And so if something has a force and pushes over a distance, doesn't it do work? Doesn't it do energy? Couldn't we take heat, like gasoline, and burn it, get it hot, and push the car?
Yes.
And that's where we're headed here. We're headed to somewhere along the lines of something like this. I take a piece of gas. Maybe I'll close up the container. The gas is in here. Can't push it down because there's molecules. Can't pull it up because the molecules are above it. And so there's my gas. I take some gasoline. I put it in here. I burn it. The gasoline gets hot. The molecules go faster. They push the car. After it pushes the engine, I let the gas out or cool the gas down. After it cools down, I heat it up. And I push the car again. And then I cool it down. And so there is our thermodynamics in action. What are we after? And so that's why this number in units of joules and in terms of energy will probably become more useful to us. How much energy is that in gasoline? Now that I burnt a whole gallon of gasoline, how far has my car driven? And so, like I said, that's where we're headed. Simply put, all of this then rewritten comes down to probably the form that you recall from Physics 102 or from your chemistry, putting the volume on the other side. PV equals nRT. That is the mathematical relationship between the pressure, the volume, the temperature, the number of molecules, or I really should say the number of moles, and this universal gas constant. Okay, and like I said, and maybe it's worth circling and putting it over here, chances are we'll use the 8.31 because we'll be working with energies in joules that way as opposed to liters and atmospheres. We'll probably have to do some conversion. And that's why I wanted you to see the conversion. So don't forget that conversion factors from 121. In fact, I will go one more step, and this will be the end of the chapter here, is sometimes, kind of makes sense, that our focus will not be on a whole group of atoms, so we don't want to do the number of moles, but maybe we want to actually focus individually and one atom at a time, or at least talk about how many atoms. I mean, it's great to talk about 1 gallon of milk, but we could just as easily think and visualize 1 gallon of milk of billions and billions and billions and billions of molecules. We just have to talk about big numbers, right? And we can do that. And so let's change this. Another way of viewing this is to not think about the number of moles, but to think about the actual number of molecules. So let's come back over here to Avogadro's number here for a moment. As I look at Avogadro's number, what would be the connection between the number of moles, Avogadro's number, and a symbol that I will use now, N, will actually be the number of atoms or the number of molecules. And so you can see the N's can easily get confused. This is Avogadro's number. This is the number of moles. This is actual number of molecules. But if I put that on to the side, how would I say calculate the number of moles in relationship to the number of molecules that I have? Well, I guess I'd take the total number I have, right? Divide it by Avogadro's number, and that would tell me how many moles I have. So if we do that here in this equation, we can actually replace the little n with a capital N. And so we would have this R divided by Avogadro's number as our constant. And it was Boltzmann who thought about that, and he looked at this and said, well, there's no point in writing two constants as the quotient of themselves. Maybe we should just do one constant. So he takes R, which is 8.31, and he divides it by Avogadro's number, which is a very big number here, obviously, coming up with a number very small. And so we will just refer to this then as Boltzmann's constant, where it would still be the ideal gas law. It's just looked at in terms of how many atoms or how many molecules do you have. And that number comes out to be 1.38 times 10 to the minus 23 joules per Kelvin there, as we kind of work out what that would be. So again, this might be new for a lot of you in the sense that we have the ideal gas law. Maybe I will put it together as a box, but here we've got, and I'll write the constant first since that's usually what we do here. So whether you want to think of it like this or like this, and I must say we'll think of it like this probably most of the time at the beginning, and then as we get into more sophisticated stuff, more like this towards the end of our thermodynamics. But this is the relationship between pressure, volume, and temperature. As a quick example, let me just show you a couple of these. Some of you who've come through chemistry, which you often learn at first called Boyle's law. Boyle's law is a very special case of this. I mean, watch what happens. I'll take this equation and rewrite it. Let me write it as pressure times volume divided by number of molecules times temperature. That equals 2R. Fair enough? So if I took a gas and said this is the initial conditions, initial pressure, initial volume, initial number of molecules, initial temperature, whatever those initial conditions are, if I put all those in there, I would get this constant. Now, if I changed the gas, if I changed the pressure, if I changed the volume, if I changed the temperature, if I changed the number of molecules, if I changed only 2 of them, 3 of them, all 4 of them, when I'm all done, I would still have pressure final multiplied by final volume divided by final number of molecules divided by final temperature would still equal R. And that's what's neat about the ideal gas law, is that equals a constant. And as you rearrange temperatures and pressures, the other parameters rearrange accordingly, and you will get that same constant. So here's what's nice about that. There are special cases. If you put these two together, if you put initial pressure times initial volume divided by initial number of molecules and temperature, then this is what will happen later on. And in the interest of time, I won't write too much more here on the board, but I'll say, I think you've seen this in terms of Boyle's law. Boyle's law is a real simple case of this. Boyle's law says, look, you have a container of gas. It's the same gas. You don't have a chemical reaction that takes place. You don't let any in, you don't let any out. So what would you say about N on both sides of those equations? Same numbers, cancels off. And let's just say we do it kind of gently here in the room at room temperature so it doesn't get warmer, it doesn't get colder. What would you say about the temperatures?
Same.
They're the same. And so many of you are probably familiar with this special case of initial pressure times initial volume equals to final pressure times final volume. That's what you get if you don't change the number of molecules and you don't change the temperature. And so simply put, and this is our little diagram here of Boyle's law, here is my container. And it's not the best for a big room like this, but if you can see from your distance here, I've got a pressure gauge, kind of hard to see through the green, but it's pointing at 15. The volume of gas is actually in this syringe here. What do you think would happen if I were to squeeze the syringe and make the volume less? Yeah, so right now I have a certain pressure and volume. And if I come along and make the volume smaller, what happens to the pressure? It's got to go up. And so if I were to cut the volume in half, the pressure goes to 30. Right? Doubles. Goes from 15 to 30. If I were to pull down on the syringe and pull it to twice the volume, if I can. I don't know if you can you guys see the gauge there? At least you guys in the front? and the gauge would go down. And so there's a direct connection between pressure and volume. And so that's, like I said, something that I think you've come from your background in chemistry, and particularly like a high school chemistry, where they get into Boyle's Law. What I want to emphasize is we're doing something far bigger than that. It's not just Boyle's Law. Yes, Boyle's Law is true, but this is better. Right? This tells the whole picture. Okay? Another scenario that can happen here. You probably know this as Charles' Law. What if you don't change the number of molecules? Let's see, Charles is constant pressure? Pretty sure. Constant pressure. And so what if we do a little experiment where we don't change the pressure on the gas? Well, I'm hoping you'll see that, okay, the two ends would cancel off and the two pressures would cancel off. And so you would again have the special case, a relationship between volume and temperature. And as you can see, I'm not real focused on the individual special cases. It's the bigger picture. See how that works? And then we can do a subset of that. And so this is just simply saying, what if you have a gas that has an initial volume and initial temperature? In fact, that's what you already saw me do over here. You saw me take this gas, which is at an initial volume of this container. It's at room temperature. What I did is I let a certain number of molecules in and then closed it. And so if you look closely at this, I have molecules in here and then a tube that contains it in there. So you might say the volume is this plus the tube. Okay. And so there's my volume. And its temperature right now is roughly room temperature. But what if I warm it up? What if I put it in the hot water? Yeah. Keeping the same pressure on it, which happens to be the weight of this piston, means that as the temperature goes up, its volume goes up. And isn't what that math saying that? Or if its temperature goes down, and so here's the ice water. I guess I should have shown you the ice. But there's the ice, and then the volume goes down. So again, a direct connection between those two parameters. But it's a special case. Oh, you probably learned a third one. Who was the third set? Gay-Lussac? I hope I'm pronouncing it right there. The two of them. They did this. What if you had same number of molecules, but same volume? What would you get then? Now, again, a special case, but you would see pressure is related to temperature. And so that's what this would reduce down to. So again, I'll say it again, I'm not so interested in these individual cases. What I do want to make sure is you see the mathematical connection between all of the parameters, the pressure, the volume, the temperature, and the number of molecules. Chances are for us, I don't know if we ever change the number of molecules, maybe a little bit, but that's more of a chemistry question. We have a certain material and we have a chemical reaction, and then the number of molecules change after that. So important, but not something that we usually study quite at this beginning level of our thermodynamics. And again, probably the best example of that is right here. This is a pressure gauge. It happens to be at 15 psi. Unfortunately, it's psi, not pascals, but it's at 15. Here's the volume. Okay, the volume is fixed. Number of molecules is fixed because it's got a little valve here that I've closed. What do you think would happen if I put it in hot water? It's going up. There we go. Right? And so as the temperature goes up, the pressure goes up. As the temperature goes down, the pressure goes down. And there's a direct connection between them.
So
yeah.
We're talking about the number of atoms, not the number of molecules, right?
It's really number of molecules, I guess, because if I had, say, nitrogen. Nitrogen, if you remember from chemistry, is a diatomic. So the two atoms are hooked together. So they count as only one bouncing BB. So it's the whole molecule. If I had H2O in the gas phase, it's not the number of atoms, it's the number of molecules. It's the number of, I got to think of those as one big cluster bouncing around.
So the Avogadro's number refers to the number of molecules?
Yeah.
The number of things you have.
It's the number of things bouncing around. So I should be a little careful here, yes.
You have N as atoms.
Yeah, okay. Because it could have, yeah. Here's where I run into trouble. If it's helium, then it's the number of atoms. They're not diatomic. If it's oxygen or nitrogen, then it's the number of molecules. And so most of the time it is molecules. The exception would be when I'm using the noble gases, then they're atoms. But I think Max said it well. It's the number of objects bouncing around. So yeah, I should put molecules here. Anywhere else I got atoms? That's moles. So how many things are bouncing? Yeah. And making the pressure and making the volume. Yeah. Well, as examples then, let's turn to the back of the book here and see if we can do a few of these and see if they'll make sense. This will be your homework over the weekend and give you a chance to kind of work through this. And I have a calculator that has no batteries. Can I beg, borrow, or steal a calculator from anybody? And I'll run through some numbers here. All right, thanks. All right. All right. Ooh, I'm going to get them confused. Yours is one with good batteries in it. All right, so I'll start with number 10. I think number 10 has a good one to get started with. I think this brings us back to thermal expansion stuff, if I remember. And basically that is kind of the two sets of calculations you're going to be doing. Is your thermal expansion, how much bigger or smaller does an object get? And then the other one is these ideal gas laws. How much new pressure do you have, or what's the new volume of it? As I said, number 10 here says something along these lines. Yeah. It goes back to what we were talking about on Tuesday with the expansion and things getting bigger. And here's a good manufacturing process. As I talked about, it's good to maybe heat something up and put it on and let it cool down, or cool it down and put it together, and as it warms up, they fit together. Here's what it says. It says at 20 degrees Celsius, so room temperature, an aluminum ring has an inner diameter of 5.0000 centimeters. And a brass rod has a diameter of 5.0500 centimeters. All right. So I have a ring where this inner diameter is 5.00, and I think they list 4 zeros there. Okay, so it's trying to say it's 5. Okay, it's close to 5. It's 5 centimeters for its inner diameter, and it's made out of aluminum. But then, in addition to that, we have a brass rod, and it has a diameter that is 5.050 centimeters. 1, 2, 3, 4. I think there were 4 decimal places.
Do you need to have all those zeros in front of the 5?
In front of the 5?
Because it's 5.000. I mean, yeah, in front of it. Like, but it's 5 point and then 4 zeros.
Right. So they're trying to say in terms of significant figures, you know it's 0, 0, 0, 0. It's not a question mark. It's not an I don't know as we did. Okay. And but to answer your question, yeah, we're going to have that many significant figures because it's going to change its size, but not by very much. It's not going to go from 5 centimeters to 6 centimeters. It's not going to get that big, okay? You'd have to warm it up pretty warm. It would melt by then, okay? All right, so there's the rod. And you can see then that the rod and the ring are not going to fit together, right? The rod is a little too big. But it says here in the problem, A, if you only warm up the ring, at what temperature must you warm up the ring so it'll just slip onto the rod? Okay? So obviously what's going to happen here is you need to warm it. And I picked this one because I did think it was a good illustration of what I was trying to tell you. It's a nice manufacturing process. You warm up this ring, what happens to the hole? Does the hole get larger or smaller? Right, I mean, you saw that demonstration, right? The hole actually does get a little bit bigger. And so we got to get it big enough by 0.05 centimeters in order for it to slip on. That's how much. And once we get it that warm, we can then slide it onto where we want and then leave it there. And as it cools down, oh, it's going to be under a lot of tension and a lot of stress. And it's going to stay there pretty well. It would take a lot of pushing and pulling and tugging to get it to move. We wouldn't have to glue it or weld it or bolt it in any sense, at least up to some limit. Yeah.
So it's actually stronger than the weld theoretically?
It can be. I'm not sure this is enough difference that it would be stronger than a weld. It doesn't seem like this is enough difference, but I'm not sure how strong this is going to be. But yes, they can be. Very, very strong. Essentially, they clamp together so tight that they essentially weld themselves together under the pressure. Maybe that's probably a better way of explaining it. Yeah. And so they're just, hooked together like, the same thing as sandstone. If we're back to a geology example, you have all the sand on the beach. It washes out to the beach. Millions of years later, it goes down. It gets pressed together. It's not sand anymore. It comes up as one big rock. It's been pressed together. It's been welded together. It is stuck together. It's little pieces of sand. It's sandstone. Okay. Okay, so coming back to here, I think you see the idea anyways. And then that's the bigger picture. What? Oh.
I was trying to figure out if that was a 7 or a 9.
Oh.
Yeah.
What?
The centimeters on the brass rod is connected to the 0.
Okay, well, all right. Centimeter. All right. But pulling out of our hat this calculation here, this is our expansion. And I'm only going to need a one-dimensional expansion, right? I'm just going to do the diameter, because when this ring grows in diameter, of course it grows in the other dimension's diameter, and of course the area grows in proportional to it. So you could look at the expansion of length, one-dimensional, or you can look at expansion in terms of area. I think it's easier, though, to do length here. And I want this aluminum piece, this open hole, to grow by 0.500 centimeters. That's the idea, right? How much does it grow? How much temperature do I have to give it to make it increase by that much? Now they tell me it's aluminum, so I need to jump back over here and look at what was that expansion coefficient. And for aluminum, it's 24 micro. So 24 times 10 to the minus 6 inverse degrees Celsius. And we're saying it again, but as we said in class, what does the 24 micro mean? It means aluminum would grow by 24 microns for every degree for every meter you have. Okay? Now we don't have a whole meter, so if we warm it up 1 degree, it's not going to grow that much. But on the other hand, we're going to warm it up a lot more than 1 degree. So we are going to get it to go more than 24 microns. But that's our alpha. Our original length here is 5.0000 centimeters. And what, of course, we are after is this. How much do we need to warm it up? So once you see the physics behind it, now this becomes more of a plug and chug here. 0.05 divided by 5 divided by 24 times 10 to the negative 6, coming up with about 417 degrees Celsius.
What is it?
Okay, so I'm going to have to warm it quite a bit, yeah?
Is there the inverse of Celsius?
Yeah, those are the units of alpha. If you look in the table, they'll say alpha is 24 times 10 to the minus 6 inverse centimeters. Inverse degrees Celsius is how they have it labeled. Now what they mean is degrees Celsius on the bottom here, because we're going to have change in temperature in Celsius, and then that will cancel off. Well, in our case, I don't want it to cancel off. I want my centimeters to cancel off, so that when I move this to the other side, I get degrees Celsius in the numerator. So I'm going to have to warm it up by 417 degrees Celsius. Or I should say 417 Kelvin, because a change in Celsius and a change in Kelvin are the same.
That's what I was going to ask, is can you use Kelvin instead of...
Oh, right. So if you prefer, this could also be 24 times 10 to the minus 6 Kelvin inverse also. And if you remember the lecture, I guess it was a week ago, before the test, I said, remember, the change in Kelvin and the change in Celsius are the same. So most of our equations really are based upon the Kelvin scale, because the Kelvin scale is the one that has motion directly related to its temperature. And so you could argue that this is really Kelvin. However, since we're talking about a change, it won't matter whether we talk about Kelvin or Celsius. But, the thought process in my mind is Kelvin, because Kelvin goes with motion, and size goes with motion.
In reality, wouldn't that be a little extra, because you go increase the length one way and increase the length another way? Would that hypotenuse be more than 0.05 centimeters or whatever you need to get into the circle?
What do you mean hypotenuse?
Because it increases in both ways, in area and length and height.
So when
you increase by 0.05 in one way, and increase 0.05 in one way. The other way, height, once you get extra.
No, this rod then, or this ring, excuse me, would now be a little bigger this way. And then the thickness of it would be a little more thickness. So maybe in this dotted green line would represent what the ring looks now. But that would give me a big enough diameter to slide on here. Yeah. Now, granted, it's three-dimensional. I don't know if that's what you're talking about. Whatever the thickness of this ring was would also be a little bit longer.
Well, I was just thinking the effect of it's expanding in the length, and I was thinking the expansion in the height would also be.
Yeah, but I need that for this too, right? Because this is actually this high and that wide. So that's why I need this to open up in length, which is all I calculated. But at the same time it's opening in length, it's also opening in height. So the hole fits on here. So again, and like I said, this is a manufacturing process. It would perfect now. It would fit on. And again, I think that's what you saw with the brass ones I was using. I like what they add to this. They said, well, what if this? What if both the ring and the rod were warmed together? Because there is a challenge here. I mean, here's the big challenge. You're going to take this rod and warm it up. Now, that's quite a bit, right? How are you going to put that on there without the risk of it cooling down? I mean, it wouldn't take much. You heat it up, as soon as you pull it out of the oven to put it on, guess what's going to happen? It's not going to fit. Bummer. Now I suppose you might say, well, I'll warm it a little more, maybe I'll go to 500, maybe that'll give me enough time. Okay, and so if you're pretty quick at pulling it out and put it in the right spot just in time and then letting it cool, you'll be okay, right? But it would be so easy to accidentally bump it, and as soon as you take that ring and you bump the brass rod, that's going to transfer heat. It's going to cool wherever you accidentally bumped it as you were sliding it. Oh, I didn't want it there. I wanted it there. What am I going to do, right? Or if you already put it on in the wrong spot, how are you going to get it off? So a lot of these are done together. Let's warm both of them. Let's put both in the oven. And now they're both at a high temperature. And here's the neat thing about it. Since aluminum expands or has a thermal expansion coefficient greater than the brass, even though both of them are getting bigger as you warm them, at some temperature, won't the hole inside the aluminum be big enough? And you can keep them in the oven. Now, you can then assemble them in the oven, set them carefully and accurately where you want them, and now let them cool down together. And you don't have other complications of one getting hot, one getting cold, stress on one part and stress on another. Now, that's going to be a higher temperature, right? And so that's this next part of the question. It's a little bit harder. That's why it says here, what if both the ring and the rod are warmed together? At what temperature must they reach so that they fit on top of each other? So, let's try it again. But this time, they are both going to warm. What temperature is that? All right, well, again, thinking about the opening of the aluminum, I guess I would write it this way. The L of the aluminum would be the initial size of the aluminum plus the delta L of the aluminum, right? And the size of the brass must be the initial size of the brass plus the change in length of the brass. And so as we work this out, we will have the initial length of the aluminum plus alpha of the aluminum plus the initial length of the aluminum times the delta T. Down here, I will have the initial length of brass plus the alpha of the brass times the initial length of the brass times the delta T. And they would have the same delta T. They're both, at room temperature here when we get started, and then I warm them up to the same temperature. They're in the same oven as I assembly them. And so the real key is right here. I want those two to be the same length. And maybe I should say diameter. I'm saying length, and maybe that's what made you think about, the length of the rod. I don't care how long the rod gets. What I care about is the diameter. And so as I factor this out, I get L of the aluminum is 1 plus alpha of the aluminum delta T equals to L of the brass. So I'll take the L of the brass and factor it out, and it should be equal to 1 plus alpha of the brass times the delta T. I don't know, maybe I shouldn't even have factored it. Nah, I shouldn't have factored it. Oh, well. Because I know these numbers. What's the point in factoring out numbers I know? So I'll do it this. L of the aluminum. So the aluminum is 5.000 plus the alpha is 24 times 10 to the minus 6. The aluminum, again, is 5, and then delta T. So that would be that equation. And that's supposed to equal to 5.0500 centimeters plus the alpha of the brass. Well, there I need to look up what is alpha. And like I said, hopefully it's less than aluminum. Otherwise, if it's more, the brass is always going to be bigger. It's never going to catch it. But fortunately it is. The brass is only 19 times 10 to the minus 6. So it's 19 microns. There. And so there's my alpha. And then 5.0500 and then delta t. And so, yeah, I've got a little bit of algebra to do. I guess I will subtract 5 from each side. 0.0500 goes there. If I put these two together, what the heck do I get? I get a 19 times 10 to the negative 6 times 5.05. This one coming up to be 9.595 times 10 to the minus 5 delta t. Over here, 24 times an even 5 is 120. So does that make 1.2 times 10 to the minus 4? And then that's a delta t. And so finally, a little more calculator work. I can take this number and subtract that number, 9.595 times 10 to the negative 5, and get 2.405 times 10 to the minus 5, which is 0.0500. And so now I've got 0.05 divided by that last answer I got, and we are looking at an increase in temperature of 2,079 degrees Celsius, or degrees Kelvin is how much I need to warm it up. Which is a bit problematic, because then it says, will this process work? No, why not? Yeah, they'll melt by then. So the brass will melt first and then the aluminum, but they will both melt. So, and so you'll just have a molten mess here. So.
The ring first, and then once it gets there, put the other one in the oven and combine it before that one heats to...
Well, right. So this is not going to work, this process. So you have to heat just the ring and take it out real quick, or put the rod in the oven real quick or something. And you know, you got to, hopefully the rod won't warm up very fast, or hopefully the ring won't cool down very fast here. And you can still process it.
Why do they subject metals to a heat treat? What does that do? When they like put a metal into, like put it to a ridiculous temperature to make it stronger? Yeah,
when you cool something down, you see it best in ice. If you do something like this, let's say I have a liquid and I cool it down, these atoms will all hook together. Actually, might not do this. They'll make a nice little grid. They'll hook 1, 1, 1, and 1. Meanwhile, the same thing is happening over here. These are hooking. When these solidify and these solidify, they don't line up. That's where the weakness of the metal is. These are the grains. This part of the metal is very strong. This part is very strong. The metal will break because between them. So what you want is you want to minimize this as much as possible. So by reheating it, what will happen is get these hot enough that these will start to come in a microscopic liquid stage, if you will, and start to reform and hook together in their normally natural, strong pattern.
So you get it strong enough for the shear to move, but not strong enough for, maybe I'm using that word wrong, but strong enough for those breaks to move, but not strong enough to melt the already strong places.
I guess I would say it this way. If I just took a regular piece of metal, right, particularly if I took it out of the oven and put it in cold water, that's a quick cool down. And what will happen is I will have areas which we'll call grains that may be this size. And a metal that is cooled down slowly might have grains that are this size. And because the weakness is along that boundary, there is a lot more weakness in this one than this one. So how I cool it down is important, or in this case, how I rewarm it to help make something like this begin to look like that. Yeah, and so that's why that's the heat treating of that. And it'll be a lot stronger when you're done. Or something that is cooled down really, really slow. Again, somehow we got in geology and I can't get away from it, but this is Yosemite. This is Yosemite Valley in a nutshell. Those granite rocks, as we talked about, they cooled down and took millions of years to cool down, more so than any other granite rocks found anywhere in the world. What does that mean? That means that the size of the grains in the granite in Yosemite are bigger than anywhere else in the world. It means the rock is stronger than any other granite. And they call this Yosemite granite. You can't get granite stronger than that. And in fact, if it wasn't for that, you could never have, if you've ever been to Yosemite, you've got El Capitan that is 4,000 feet tall. The rock below it supports 4,000 feet of granite. Normally granite can't do that. Granite would normally crush. And if it wasn't for the extremely long cooling process, we would never have Yosemite Valley. Yeah.
Is that the same as tempered steel?
Yes. Yeah. Yeah.
So, I mean, obviously, like, we can't wait around millions of years if we want to heat treat something.
Sure.
But do we have the technological abilities to have the molecules interact in a way that they would if they were cooling down over a million-year period to get larger grains, I guess, and a better homogeneous?
Well, I like where you're going. What you're saying is that, okay, how can I make stronger metals, right?
Yeah.
Right? And the process of making stronger metals is by making sure that I cool it in such a way that the atoms stick together. And we do have processes, and that's where engineering is right now. If you want to make a stronger metal, you got to make these things bigger and bigger. Are we even close to making one big metal piece of solid grain? Oh, absolutely not. If we could, you could make, car frames out of steel that were probably as thick as your pencil lead. And it would be as strong as the current frame of steel. It would be amazingly strong. So yeah, it's a constant area of research and a constant dream of getting all these things, hooked together in such a, could you imagine riding a bike that had a frame about the size of a pencil lead?
Yeah, but would that be still be
But it would be stronger than your current bike.
But would it be lighter or?
And it would be lighter because you'd have that much less material, right?
But isn't it more dense?
Yeah, so
No. I'm not changing the density of them. The spacing between the atoms is still exactly the same. So the point is, we're not really taking advantage of our future. But
Better nanotechnology.
that is what nanotechnology is doing right now. Nanotechnology is going down that road. If anybody's heard the magical stuff, graphene, the material to change the world. Because it really is, of course you're on a microscopic level already, but you really are taking the full strength of the material. You are not ever hooking it in a pattern of hexagon. Today when we make graphite, we have a hexagon pattern and then a hexagon pattern, and we put them together, just not that strong. And that's where our weakness is.
How are you able to set those two equal to each other?
Okay, so this is the length, and when I mean length, I mean the diameter of the ring. And this, although I say L for length, what I mean is the diameter of the brass. And I set them equal because that's what I'm trying to fit one on the other, and they fit on when they have the same size. Yeah. So that's the key physics step, to set those two equal in sulfur temperature. Now, good, that was a fun one. Yeah, and a fun little discussion off the side there. A little bit of material science mixed together with a little geology there. All right, another good example. 43. Is it getting warm in here? No?
46 band.
It's just, okay. Of this side? No, I guess it only says. We got to get cold from this one? Yeah, all right, I'll leave it. All right, if I'm the only one hot, that's cool. I just was afraid you guys were going to get warm too. All right, so I'll go to number 43 here. 43, I think, again, is another thermal expansion one and brings up some interesting questions. And again, maybe this is maybe more to manufacturing, or at least the first thought that comes into my mind here. Next page. Is it says this, that you have a copper rod and a steel rod, and they are different in their length by 5 centimeters when it is at 0 degrees Celsius. All right, so we have one rod and we have another rod. I don't know which one is the longer, at least not yet. But I do know that one is a little bit longer than the other by 5.00 centimeters. Okay? One a little bit longer than the other. That's what it says. Copper rod, steel rod, different lengths by 5 centimeters. Now, the rods are warmed and they're cooled together. Is it possible that the length difference of 5 centimeters remain the same? You see, here's an interesting challenge. What if you're manufacturing something like an engine block, and you take this engine block and you put a drill through it? As you are drilling through it to make these holes, what happens to the drill bit? It gets warmer, and as it gets warmer, it gets bigger, and it doesn't drill the right hole, or it drills a hole based upon what the temperature is, and that can have variations. Of course, we use these cooling fluids and cutting fluids to try to alleviate that and to keep them at the same temperature. But as you are in the manufacturing process, you might have something and you're holding here and you're cutting it, and the blade is coming in. What happens if the blade warms up? Gets a little bigger and cuts a little more off. And so the exact size that you manufacture is really problematic because the temperature changes.
Is the exact size really that matter that much?
Well, maybe the material warms up a little bit too. So the question is, it's two parts. Number one, is it that much? No. So if you're not really that interested in how much it expands and contracts, if you're not interested in a real good accuracy, no, it's not important. And many of the things we manufacture aren't that important. When I go to Lowe's and buy a couple of bolts and screws and nuts, it's a 1/4-20, meaning it's a 1/4 inch wide. Big deal. It's slightly bigger than a quarter, slightly less than a quarter. It doesn't matter. But yes, some things significantly matter on that size. And the temperature during the manufacturing process is critical. The parts in your computer are critical. When they were made, how big is that microprocessor? And the silicon that makes the transistor is very, very important. And you said, well, they're both going to warm up. Fair enough. That will help make the difference smaller, but they're probably different materials. You're not going to be cutting a piece of aluminum with an aluminum blade. Right? You're going to have a much harder blade, and it'll warm up different. I mean, it'll expand differently, even if they warm up the same. So yeah, it's a big challenge. And so here's the answer. Could we build anything that would always be the same difference, regardless of what the temperature is?
Yeah.
We can. That's what this problem is about. Yeah. Do you see it? How could we build this? How could we have a difference between these two that is always 5 centimeters exactly, whether it's at 0 degrees, 10 degrees, 20 degrees, 30 degrees, 40 degrees.
The metal alloy, just the red mixture.
No alloy here. This just brass and steel.
The length ratio between those is because of the ratio of alpha?
Yeah. Do you see that the amount of expansion depends not only on the temperature difference, but we would say they're the same for both, but doesn't it depend on how much material you have and the alpha? So if I were to write this equation out for brass, and I would write this equation out for, what was the other one, steel? Copper and steel. Steel. Is it possible that the change in length of a brass rod be the same as the change in length of a steel rod? For the same temperature difference. Yes, if what? See, doesn't the expansion depend not only on the alpha, but also on the length of the material? And so here's what I'm saying. I'm saying that if I look closely at this table, the expansion coefficient of brass, I'm pretty sure, is more than steel. Steel is 11, brass is 19. So if I make this shorter one out of brass, and the longer one out of steel, that smaller number compared to here, coupled with this bigger number compared to there, those two numbers can be the same. And would they grow by the same amount? Because again, what determines how much they grow? Well, obviously their temperature, and obviously the alpha, the material, but also how long they are. So if I'm real clever here, I can cut myself a piece of brass and a piece of steel, set my experiment between the two, and as it warms up, the experiment is still within a 5 centimeter box. As it cools down, the experiment is still within a 5 centimeter box. And the size of the box does not change on temperature. The position of the box. The box is based upon the difference of the material. So again, another neat clevering technique, and so that's why I thought it would make a good example here. And here's then the question. I don't think I read the rest of the question, but it simply said, the rods and rods are warmed and cooled together. Is it possible that the length difference remains constant for all temperatures? Please explain. Describe the lengths at 0 degrees Celsius precisely. Can you tell me which rod is longer? Can you tell me the length of these rods? Yeah, it can be done, right? And the longer one has to be steel, right? And I could even calculate the numbers. Let's give it a try here. Here's what I know. I know this, that the length of this brass one is going to be the initial length of the brass, right? See if I'm saying this right. I'm probably making it too hard. I guess I really just want these two to be the same. Should I just jump right to there? Okay. And so you can see that if I'm changing the length of the brass and I'm changing the length of the steel, what I really want then, I'll erase this, is that the alpha for brass times the original length of the brass equals the alpha of the steel times the original length of the steel. And we looked these up. If I remember right, this was 19 times 10 to the minus 6. And this was 11 times 10 to the minus 6. Let me just double check that. But those are our brass, 19, yeah, and steel, 11. Okay? 10 to the minus 6 cancels off on each side. That's not a problem. I'll just move this. So 19 over 11 times the original length of the brass piece must equal the original length of this steel. So again, you can see in the math, the steel has to be longer than the brass. You take the length of the brass, you multiply it by 9/11, and that's the length of the steel. And so you take any piece of steel and brass that have a ratio difference of 19 to 11, then they will keep the same difference between them. And in this case, we want that difference to be 5, so only a certain length would be appropriate for 5, and it would always stay 5 between them. So that's the next step, yeah.
You stating that the alpha and the length of brass equals the alpha and the length of steel, does that imply that a change in length in brass over a change in temperature equals a change in length in steel over the temperature? Can you do that? Like, so just divide delta t on the other side.
Okay, so divide here, yeah. But I'll keep it simpler. What I'm saying is the change in length is the same for both the brass and the steel. I'm saying these two are equal. So if I did a couple of steps here, I'd say I want this so that the change in the length of the steel is equal to the change in the length of the brass. That's the physics step. I want to make sure that when they both grow, they grow by exactly the same amount so the difference doesn't change. Then substituting this in, I get alpha L delta T for brass equals alpha L delta T for steel. And they're warmed up together, so then I have this for steel equals this for brass. And that's where I started. What do you mean by the same ratio? Oh, sure. And I would do the same thing. If I was looking at the volumes of them, I would have the change in volume is equal to 3 alpha times the original volume delta T. Well, let's see. I guess for brass, I would have a 3. It'd be 19. Yeah, I guess it would be 19 over 11 for volume change. However, I would be a little careful with the volume because the volume would be made out of length, width, and height. And so that doesn't mean that the lengths are 19 to 11. Yeah. I guess, you know, keeping it a cubic in shape, it would be the cube root of 19 over 11 for their lengths in order for their volumes to remain the same. Yeah.
Volume-wise at the same rate, they need to be the same shape, because if you have a cone and you heat a cone uniformly at the same temperature, the top of the cone has less.
No, I mean,
Will it? Or?
yeah, no, the volume, if you have something that's long and skinny versus short and fat here, the volume growth is still the same. It's just when it's long and skinny, most of the volume is in its length. When it's short and fat, it doesn't grow very long here, but it grows more.
The same, it's just dimensional.
Right, right. Or at least approximately the same, because remember we said beta was 3 times alpha. Approximately. We did that expansion on it and ignored higher order terms. So, approximately. Yeah. Well, I tell you what, in the interest of time, let me not actually do the calculation, but to solve this, we need another equation, and that's where we got started, is we started with saying that the length of the steel and the length of the brass were already 5 centimeters apart. Yay! So there it is, 2 equations, 2 unknowns. And that will tell us then how long of a piece of steel and how long of a piece of brass do we need in order for them to be, 5 centimeters apart. And then if they are that length, since it's a ratio of 19 to 11, when you warm them up, they will always stay that same length apart. And so, like I said, nice little tool. Here's a fun one. Let's do number 45. 45 says this. It says, take an object back in chapter 10 that has a moment of inertia. Oh, yeah. How about a disk? It says any object. All right, I'll do a disk. Actually, why don't I do a sphere? Sphere will be a fun one to talk about. For some reason, I just can't get geology out of my head, so we'll talk about the Earth here. All right. So we'll do the Earth. All right. So here's the Earth. Here's a sphere. Now you learned, although it's been some time ago, so maybe I should just kind of recall. What's moment of inertia? Okay, it's its resistance to rotate, right? It's the equivalent of regular inertia, right? When you push on something, it resists it because of its mass. It doesn't want to go faster, it doesn't want to go slower. So if you have an object and you want to spin it, it resists its spinning. Or if it's already spinning, it doesn't want to stop spinning, like the Earth is already spinning. And fortunately, it doesn't want to stop spinning. It just keeps spinning and keeps spinning here. It has a rotational inertia. If it is a solid sphere, its moment of inertia, I was going to put on the board, but maybe I should even ask. Well, there's an m, definitely. And there's an r squared. Good. Good for the prefactors. I heard someone say 1/2. That was a cylinder, so good guess. We use that one a lot. We didn't do the solid sphere too often, but it comes out to be 2/5, and I'm sure that's why your author says go back and look in chapter 10. So go back and look in chapter 10, pick an object. Pick a cylinder, pick a solid sphere, pick any object you want. Maybe I should ask, you remember a rod? Good. 1/3 around the edge and 1/12 around the middle. Perfect, right? And so that's the moment of inertia of a rod. But in this case, we have I'm going to take the solid cylinder. But here's the question. Here's the interesting part. What happens when it warms up? It gets bigger, right? And so what does that do to the moment of inertia? Yeah, and if we put that together with conservation of angular momentum, if we have something like the Earth, and the Earth warms up, and it expands, does that change the rotational inertia? Yes. So then does that change the rotational speed? Yeah, and for those of you who might remember from 121, you might remember, I think I was standing on a stool here, spinning around, I put the weights out, what happened? Slow down, pulled the weights in, what happened? And faster. And so the amount of speed depends upon it. And again, for whatever reason, we got into geology last time. But this is a good example, because you've probably heard of sea levels rising, right? Why is the sea level rising?
Because the Earth's spinning slower.
Why is the sea level rising?
Polar cap.
Yeah, most of the time you hear that the ice and the polar caps are melting. True. But less than half the reason true.
Ambient temperature of the ocean.
The temperature of the ocean is rising. And when the temperature of the ocean rises, what happens? It expands. We will get more rise in the ocean due to thermal expansion than we will from the melting of ice in Greenland and the polar caps. And so most of our expansion is coming from thermal expansion. Now that wasn't true about a decade ago. Most of it was because of melting of ice. But what we have today is most of the rising of sea level is a thermal expansion issue.
So if the Earth is orbiting the sun and it gets far away from the sun, does that mean that our days are going to change in length?
Careful what you're saying here. This is the spinning of the Earth. The day is based on the spin,
Right.
not the orbit.
But if it gets far away from the sun, then we get less heat energy, so the Earth would cool. So that would change its size, which would then change its...
Oh, okay. Fair enough. I think we would have a lot other problems if well, depends how far we moved away, I guess, right? But I would say that for anything that makes the Earth warm or cool. So if you moved closer to the Earth, to the sun, you would warm. You move further from the sun, you would cool. But that's not the main reason why we tend to warm and cool on Earth. We tend to warm and cool because of the change of the
Radiation.
chemistry of our atmosphere. And so there have been times in the past where we've had very little carbon dioxide in the atmosphere. And a consequence of that, we had the whole Earth covered in ice. Okay? Covered in ice, at some point, the volcanoes... God, we're just a total geology class here today. This is terrible. No, this is good. No. But at some point, the volcanoes popped through, releasing a lot of carbon dioxide, warming it, and then melting the ice cap. So we've gone through periods of ice. That was the extreme case of the whole Earth covered with ice. Most of our ice ages, the ice comes down to about Montana, and then retreats back into Canada, and the ice ages are,
The other way too, doesn't it? Weren't there like deserts in the Dakotas and?
Yeah. So right, and that seems to be the direction we're headed. right? And then the debate still is out there, is it from all the greenhouse gases from our fuels, or is it nature and all of its carbon dioxide from all of its volcanoes and stuff?
How does the ocean expand? I mean, normally when a liquid gets hot, does it really expand? I mean, like water?
Yeah, didn't you see me do the scale? Oh yeah, you weren't here, but you saw it enough that we measured 0.5 gram. The liquid, when I did the buoyancy force up there, the liquid actually got a little bit bigger. In fact, there's a problem coming up here. Well, we'll do example and calculate how much the liquid expands.
Not very much though.
Wait a minute, how much depends upon?
We can actually see how much.
Doesn't how much depends upon how much temperature, what the material is, and how much length it is? So if you're looking at a long length, like an ocean that is 1 mile deep or more, right? You really don't have to have much temperature difference or a big coefficient in order to get a couple feet to rise. And that's what we're looking at, right? So that's our rise. And I don't know the number, how much, but 2 or 3 feet of sea level rise that is predicted in the next century. I think the 2 or 3 feet is thermal expansion. Well, there's another foot or 2 from the melting of the ice. Well, you don't see too much of it because you don't have this much of it. Yeah, now you have a whole ocean full of it, right? And it's added with the fact that not only do you have a whole ocean, and it only ends up with 2 or 3 feet. You think, oh, what's 2 or 3 feet? It's really not too much here in Santa Barbara. But if your whole country is on an island that has nothing higher than 2 feet, it is a big deal. I mean, it's like no more country after 2 feet of rising. Yeah.
Does water and ice have different rates of heat transfer?
Yeah, sure. Yeah, water and ice are different because their molecules are locked up a little different. All right, well, anyways, I better hurry with this one because I do want to show you the other ones here. But the point here is, here's what would happen when you warmed it up. Once you warmed it up, this radius of the Earth, or this radius of the sphere, whatever is rotating, once it warms up, it is now a little bit bigger. It is a little bit bigger by this equation. And so this problem says how much bigger is it? And so if we look at the expansion of the radius, this is the change in r. It is the alpha times the original length or original radius times the delta t. And so that is the extra part that expands. And so this question says, well, what percent is that? How much of an increase is it? Because as you say, you can argue, it's not much. Fair enough. So is it enough to matter? Well, it depends how accurate you want to be. Is this 1% rise, 2%, 3%? If you don't care about 1%, then you'd say it's insignificant. If this is a spinning tennis ball during a tennis match, you probably don't care when the tennis ball warms up or not. It's a change, but not by much. If it's a spinning Earth, again, you probably don't really care too much about the change in the spin. You're more concerned about the rising sea level than you are the change in the spin of the Earth. But here's the increase here. So this becomes a 2/5 mr squared. This becomes 1 plus, and I'll write it as 2 alpha delta t plus alpha squared delta t squared. Okay. And so this is the increase, and so for that matter, that is the next increase. But again, depending how you want to do this problem, can you tell that one of these is a lot bigger than the other? What was alpha again? Because it depended on what material it was, right? But wasn't it had 10 to the minus 6s in it? If it was aluminum, it's 24 times 10 to the minus 6. If it was brass, it was 19 times 10 to the minus 6. If it was still, it was 11 times 10 to the minus 6. So what happens when you square it? It's 10 to the minus 12. So here's a millionth plus a trillionth. Is it okay if I drop this off? Right? And really just say this right here is the extra percentage increase, the 2 alpha delta t. That's the extra increase. In other words, this is what we had before. This is the increase. And so coming back to the problem, 45, do they give me the material? They say, A, assume this material is copper and you warm it up 100 degrees. What's the percentage change? All right, well, if it is copper or if it is aluminum, let's see what we have here. For copper, for aluminum. For copper, we haven't looked up copper, have we? We've been doing brass, so I bet it's pretty close. Copper is 17. So this is 17 times 10 to the minus 6, and I'm going to warm it up 100 degrees. The aluminum, we did a 24 times 10 to the minus 6, and I'm going to warm it up 100 degrees. So 2 times 17 is 34. 34 times 10 to the minus 4 there. This is 48. 48 times 10 to the minus 4 there. So that's the change. 100 degrees is not a big change for this ball. So, that's not going to be, significant. Measurable? Yes. If you have an atomic clock that can measure a billionth of a second, you get this. And so that's why we are constantly having these leap seconds. You'll hear scientists talk about, they added in a second to the atomic clock. Why? Well, because the Earth is slowing down. Why? Well, the sea level is rising is one reason. The other reason is we tend to build a lot of dams and store a lot more water up there, which again is the reason we slow down. And so the Earth keeps slowing down ever so slightly, but measurable on a billionth of a second. So that's, So, you and I would never notice it on our clocks, but nonetheless, it's there. All right. Okay, well, bummer. I wanted to get a little bit further. Let me try 46, because I've done a lot here with thermal expansion, but I haven't done much with the ideal gas law. And so you are going to be asked to do a number of problems like this, and of thermal expansion. And if I have time, I'll come back to this. But I didn't quite get to number 11. Also was my next one on the list, was your question, is what would happen if I filled a container with water and then warmed it up? Wouldn't the water expand and then flow over the edge? Except wouldn't the container expand too? So would it flow over the edge? It depends what the material is made out of, right? And so we would have to calculate both the expansion of the water and the expansion of the container. And if I have enough time, I'll go back and do that. That's a good one. But there's 2 homework problems that I know in the past students have always struggled with, because they always do the expansion of the liquid in the container, but they forget that the container changes volume also. Now, chances are they're not equal. Chances are the water, and I think the example I had, they filled it with turpentine, because turpentine expands a lot, and they put it in a brass container. And brass does expand somewhat, but not like turpentine. So as it warms up, the net effect is some turpentine does flow over the edge, but not as much as you might have guessed, because the container is actually slightly bigger. Well, like I said, we'll do an example if we get that far. But to make sure I get to an ideal gas law, I wanted to jump past number 11 and go to 46 and do a couple from there. And so 46 is this. 46 says, derive an expression for the buoyant force Buoyant force. Where'd that come from? Oh, physics 121. Oh, okay. Darn. All right, so derive the buoyant force on a spherical balloon that is submerged in the water as a function of depth as you put the balloon in the water. Now let's talk about this conceptually first. Okay, here is the container. When you put a spherical balloon in here, just below the surface, how does that compare when you are down deep in the surface?
Well, difference is pressure, isn't it?
Yeah, so going back to chapter 14, what do we know about the pressure? Yeah, we know that there's going to be a higher pressure. So, in case you've forgotten here, let me emphasize that. This is at a higher pressure than this. So we're going to start at a low pressure and we're going to sink it down. Now, let me put PV equals to nRT. What are we trying to say in this chapter? What would happen then to this balloon as it went further down into the water?
It's smaller.
There'd be more pressure on it, and so what would happen to it? Its volume's going to change. Now this is assuming the temperature doesn't change. I may not have read it all the way through, but it does say here, derive an expression for the buoyant force on a spherical balloon submerged in water as a function of depth below the surface. You can write this in terms of the volume and the pressure on the surface. Go ahead and assume that the temperature of the water does not change. All right, so as I push this down in the container doesn't change temperature, but as the pressure goes up, temperature remains the same. What happens to volume? Yeah, it goes down. So what's the balloon going to look like down here? A little smaller, right? Now let's go back to Archimedes' principle. What is the buoyant force? How do you calculate the buoyant force? What did Archimedes say?
Something like MGH.
It's equal to what? The weight of the displaced fluid. So look closely at this picture. Are you displacing the same fluid here and here? No. So is the buoyant force going to be the same? No. Where's the buoyant force going to be the largest? At the top, right? In fact, it's why I brought this crazy thing. If anybody wants to see it in action, here is a balloon. Now, it's not a spherical balloon, but it is nonetheless a balloon. And it's got a string on it. Question?
Wouldn't it be the difference of the weight between the displaced fluid and the balloon? No, the buoyant force, the difference between the weight of the object and The displaced amount, right?
The displaced volume has the density.
I'm not saying this well. The buoyant force is actually the difference between the pressures on top of the balloon and below the balloon. That's the buoyant force. And that buoyant force is equal to the weight of the fluid that would have been there. So when I have something like this, I don't know if you can kind of see because of the magnifying effect of the graduated cylinder, but I've got a bunch of weights hanging on the end of a balloon. Okay? And so the weight is pulling it down. Buoyant force is pushing it up. If you can tell, it's just slightly above the surface there. And so if I were to push it completely underwater, oops, cut my string there, try it again. But if it goes just underwater like that, you can see that the buoyant force is more than the weight and the thing floats up to the top. But just barely. But what happens when I push this balloon down under the water? What happens to the volume of the balloon? It goes down, and then the buoyant force gets smaller. Is it possible that the buoyant force gets small enough that it now becomes less than the weight? And then what happens? Then the weight wins, right? And it goes down. So I'll put the string here and give it a little nudge down. And it looked like that wasn't quite deep enough, right? It squeezed it, but it still had more buoyant force. And now, that was a little too much. So maybe there is a point right about here. No, here. Here. Still thinking. Here. Here. Oh, close. And so it's an unstable equilibrium. So I'm not going to even attempt to keep it there. And right there was the other direction. And so like putting a ball on a hill, it's going to go one way or the other depending on the buoyant force. But the buoyant force will change. And of course it has to do with pressure. It has to do with the ideal gas law. And so if we put our previous stuff together with our current stuff here, we should be able to come out with a formula here. And so that's what I wanted you to see. So let's put this together. This is the ideal gas law. That's new for this chapter. How do you calculate buoyant force? I'll go mg, but maybe I'll put the word displaced fluid here. Because again, it is the displaced fluid. And the displaced fluid can be thought of as the density, in this case it's water, times the volume displaced times g. And so there's my buoyant force. My buoyant force depends on the volume, exactly. And as we said, it should get a little bit less here. So let's try a little bit of math with this. So here's my buoyant force. Here's the density of the water. The volume then would be the volume of a balloon. nRT divided by the pressure times G. And so that's putting the two chapters together. Chapter this 14 together with 19. And so that would be my equation. Now they said to write it in terms of the volume on the surface. So let me call this V sub S for the volume that it has when it gets started. And let me call this P sub S for the pressure at the surface, because the pressure is going to be a little bit more down here. Yeah?
Why do we not take into account the chemical inside the balloon? Why does that not even matter?
The chemical inside of the balloon is not considered in the ideal gas law, because back to our model. How are we approximating this?
I mean, for the buoyant force, like we just treat it as it's like empty nothingness.
Right, because, again, I guess we'll go back to chapter 14. When we did buoyant forces, we said, here is an object underwater. Why is it being lifted up anyways? What is the water doing to lift it up? The fact that there is a higher pressure down here versus a lower pressure up here means that these water molecules down here are pushing up more than the water molecules over here are pushing down. That's where the buoyant force comes from. But your question is, who cares what the material is made out of? The force comes from where? The water below minus the water above. So that's why we don't care what this is. You could put this could be a chunk of lead, this could be a chunk of aluminum, this could be a chunk of brass. It doesn't matter what you put there, the buoyant force is still the same, because the buoyant force comes from the water. Which is, I guess, why we, and we might not have done it last semester. Did we do that very last Archimedes experiment? Yeah, I think we ran out of time. We didn't do the Archimedes one, but it was on the syllabus there. But the Archimedes one is for those of you then who were semester before that. You did that, yeah. And you might remember part of that experiment is exactly this. You put these objects in here. You put one that is made out of brass, and you put one that's made out of aluminum, and you measure the buoyant force, and they're the same. Doesn't matter what the material is made of. That, which is the point of that experiment.
It's nice for MG in your force diagrams, right?
Yeah.
You can do math times.
Yeah.
Block of brass and block of steel.
It's also why Archimedes' principle works, because Archimedes said nature has designed it in such a perfect way to support water. if you didn't put that piece of aluminum there, water would be there. And this water underneath it would support it. So that's why Archimedes said that the buoyant force is equal to the weight of the displaced fluid. Because what would have been there would have been water. And nature designed the water around it to support water. If you put something else that's heavier, it won't support it. Something else that's lighter, it'll push it to the top. But nature has designed it to lift up the equivalent of water. And so that's why we calculate buoyant force equal to the weight of the displaced fluid. Well, a couple more things to work on this. I'll start with, again, going back to chapter 14 and saying, okay, how do we get the pressure as we go down in a fluid? Anybody remember? It's the pressure at the surface plus the weight of the fluid. Rho G. Okay, Y or D. Okay, I'll put D. All right, and so there is the pressure as we go down. Oh yeah, and then last semester we got a little short change there in 14, didn't we? Yeah, we just kind of ran out of time there. Ah, bummer. Well, I'll finish this off then with this on the surface, because again, it's kind of a nice little trick here, and you're going to see this over the next couple of chapters. We're going to use the PV equals nRT in tons of ways. We'll use it one way, switch it back, switch it forward. This is the temperature, and so this could be applied to its pressure and its volume at its surface, or its pressure and volume at the bottom. They want it listed in terms of the surface. So I could then write this using the ideal gas law as the pressure and volume at the surface, because that's what nRT equals. nRT equals pressure times volume. And if we put it at the surface, that's what nRT is. And so we can answer their question about what is the buoyant force. So there's our buoyant force at the, based upon how deep it is. Let me pick one here. I think 24 might be another ideal gas law. Yeah, this is another good one here. This one says this. It says, at 25 meters below the surface of the ocean, where the density of the water is 1.025 kilograms per cubic meter, and the temperature is 5 degrees Celsius, a scuba diver exhales an air bubble that has a volume of 0.1 cubic meters. If the surface temperature of the ocean is 20 degrees Celsius, what is the volume of this air bubble when it gets to the top? And so it's kind of like this in the reverse. What would happen to an air bubble as it went up? Does it stay the same size? No, it gets bigger. Why does it get bigger? Less pressure is one reason, and what else is going on this time? Higher temperature. And so as this bubble is going up, we have a reduction in pressure and an increase in temperature. Both of those mean the volume gets bigger and bigger and bigger. And I don't know if you've ever seen bubbles going up, you know, especially if you've ever been to like SeaWorld and watched the dolphins swim and they release some air bubbles. You can watch them. They're little bubbles down here, and as the stream gets up, they get bigger and bigger and bigger and bigger. Or maybe you've seen, they'll launch weather balloons that way. They'll put just a little bit of helium in this big long sheet, because what's going to happen to this little ball of helium as it goes up 100,000 feet?
Wait, will it risk exploding? You put too much?
It's going to, oh yeah, definitely risk exploding. You got to put in just the right amount. You don't do it right, it will get bigger and then tear. Yeah. Which is what I understand happens with those helium balloons that, you know, kids have and they get loose, right? They're already full, pretty full, and then they float and float and getting bigger. Yeah, they don't go to the sun, right? So, Yeah, I know. You thought they were going to the sun. Yeah. I ruined your party. But yeah. My son has a sticker on his a backpack, and it lists a bunch of reasons not to take physics. And I forget what all of them say, but one of them says, "You will never enjoy movies again." So I saw that. Oh, you know, that is terribly true. You got Indiana Jones jumping off a rail, landing on another rail. Oh, come on. Yeah, or Star Wars with lasers that you see the light coming back, or smoke in the outer space when it burns. Yeah, I'm 3 scenes behind. Oh, they can't do that, honey. Shut up. I'm trying to watch the movie. All right, but they can't get there. 3 scenes ago, it didn't make sense. All right. But back to this, and what we did earlier, there was our ideal gas law. That if you took the pressure and the volume, you multiplied it together, divided by the number of molecules and the temperature, you would get R. And that would be the same thing that you would get a little bit later. And so if pressure, temperature, and volume all change, it would still equal to R. So the case we're working on would look something like this. We would have some initial pressure, some initial volume, and some initial temperature. I'll put in the initial number of molecules, but that is the part of the physical problem that hopefully you connected to, is that as this air bubble goes up, all of those molecules go with it. And by the way, if you are a scuba diver or have been scuba diving, I mean, this is one of the unfortunate consequences of scuba diving, is that the volume of air is much smaller. So you put on this tank and you go really deep, but you can't be there very long because all this compressed air you had as you are breathing it in is still under a lot of pressure because you are under a lot of pressure, and there's just not that much air. And so your dive time and your tank time is significantly reduced as you are deeper. So if you're scuba diving around at 20 feet, great. If it's 60 feet, well, you're not going to be able to be as long.
So would you have to empty your lungs before you came back up?
Oh yes, and then part of the reason you have to get certified to scuba dive is because it can be very dangerous, and a very problematic and fatal mistake would be holding your breath as you ascended up, because as you ascended up, like the balloon that didn't get to the sun, it would expand and rupture. Yeah. And so yeah. So in an and one of the things I remember in my certification class, I mean, that's what we had to do. You had to practice, something goes wrong. And so, the instructor would shut off your air, and so you had to ascend to the top quickly. But the technique is it's exhale all the way up. So you release your weight belt, and you just exhale the whole way up. And that, before you can get your license, that's what they make you do.
So when they're down deep, the divers need a certain amount of volume of oxygen per minute, or a certain amount of atoms of oxygen per minute?
Well, technically, they, I suppose, only need a number of molecules. But what the reality is when you take a breath, it's a certain number of molecules. So you have way too many. And you take it, and then as you exhale, all that still is going up. That's why those recyclable ones make a lot more sense. Not cheap, but you inhale, you use very little of the oxygen. As you exhale, it goes back into your tank to pressurize it and come back in again here. And so you use all of your oxygen. And in that sense, you could be underwater a long time. You're not releasing it. Yeah.
What causes the bend?
Oh, well, the bends is, it's not quite this. It's more like a soda bottle. You ever open a soda bottle? And when you open it, you hear the fizz come up. The amount of carbon dioxide in the case of a soda. If it's a scuba diver, it's the amount of nitrogen. But the amount that goes into the liquid, which in scuba diver, it's the amount of nitrogen that goes into the blood. In a soda bottle, it's the amount of carbon dioxide in the water. But that's based upon pressure. So you can have a lot of dissolved carbon dioxide when it's under pressure. So when you open it and take the pressure off, what happens to all that carbon dioxide? It goes back into a gas. If you're a scuba diver and you go down deep, all the nitrogen that is in your blood as you come up turns into a gas. And if you have gas, which is expanding gases, at best you're just in pain. Like it's in the joints of the knees and the elbows, extremely painful. But at worst, it's death because the air in your veins, your valves only work because of the fluid that is opening and closing the flaps. And so now your heart doesn't work. It goes like this, but the air's opening and closing, and the blood doesn't circulate. Just the air that's in your veins compresses and expands, compresses, expands, and the blood doesn't move. And you'll die. Yeah, so that's the real danger about the bends. Well, I'll finish this calculation, but I got to tell you. So I was diving in Mexico years ago, and we had this huge bean traditional Mexican dinner before we dove.
Those are the best.
So all this gas that's produced in your colon on the way up becomes what? 10 times bigger? So instead of this giant exhale on the way up, it's a giant fart on the way up. Just the whole way up, just it's non-stop as you come up here. All right, but to finish this, let me put in the numbers. So down here at the bottom, they said it was 5 degrees Celsius. I wanted to emphasize, what do I put here? All right. Notice I put it in Kelvin, and that's just want to make sure you emphasize. It's a very common mistake. Hopefully you won't make it. But that temperature scale right here is based up on the Kelvin scale. When we get to the top, we're at 20. So 273 plus 20 is 293. So there's the final one. The initial, they said, is 1 cubic centimeter, so I can do that. The pressure at the top, I'm looking for volume. And one last thing here is, how do I get the pressures? Yeah, again, we're back to what we did here. Is we've got to calculate the pressure based upon how deep we are in the fluid. So they say the bubble comes up to the top. At the top, we have the pressure at the surface. The pressure at the surface is atmospheric pressure. What's atmospheric pressure? Yeah, 101,300 pascals is what I would put there at the top. But over here, down at the bottom here, I guess I would put the pressure at the top plus, and I guess I need a little more room here, I need the density of the fluid, which they did tell me it was 1,025 kilograms per cubic meter. G is 9.8, and I need to go back here to look at the depth. How deep were we? Oh, that's not 20. Which number is this? 24. 24. We're 25 meters down. Okay, so 25 meters down. But if I put in all of those numbers and those numbers, you can see the only thing I don't know is the volume, and I wish I had more time, but it'd be interesting to see how big this bubble is. What started at 1 cubic centimeter, how big is it on the surface? And again, it's bigger for two reasons. One, less pressure. Two, more temperature. All right, well, stop there. Good luck on the homework. We will start the next chapter, I guess, next week.